Welcome to The Explainer. Today, we're taking a grand cosmic real estate tour. We're going to summarize a fascinating exploration of the universe's most famous exoplanets, all to uncover the terrifying reality behind a term we hear all the time in the news, the habitable zone. We constantly hear about scientists finding these supposedly perfect Earth-like worlds. But if we actually packed our bags and traveled there, what would really happen? Well, spoiler alert, it is definitely not the vacation you're hoping for. Okay, let's dive right into this. Here's our interstellar itinerary for today. We'll be doing a rapid-fire tour of the galaxy's most promising real estate. We're starting with the search for Earth 2.0, debunking the waterworld illusion, navigating red dwarf dangers, touring the crowded TRAPPIST system, examining alien flora, and finally, answering the ultimate question with the Fermi paradox.
Section 1. The search for Earth 2.0. Finding K218b.
So our first destination is a famous planet called K2-118b. It's a massive super-Earth about 124 light-years away. The media often hails this place as a prime candidate for life. But how do we even know what's actually out there without visiting? Well, our main tool is called transit spectroscopy. Basically, when a planet passes in front of its star, some of that starlight filters through the planet's atmosphere. And because different gases absorb specific wavelengths or colors of light, telescopes like the James Webb Space Telescope can essentially read it like an atmospheric barcode. Using this exact method, scientists actually detected dimethyl sulfide on K2-18b. Why does that matter? Because right here on Earth, that specific gas is produced by marine phytoplankton. It's a huge potential biosignature, so we should absolutely go visit, right?
We'll take a look at this number. 193,399. If we hopped into the absolute fastest human-made spacecraft we've ever created, which is the Parker Solar Probe, traveling at a blistering 692,000 kilometers per hour, it would still take us over 193,000 years to reach K2-18b. I mean, this staggeringly huge number just perfectly summarizes the sheer, uncompromising scale of space.
Moving on to Section 2, the waterworld illusion, Kepler-22b.
Now, let's look 635 light-years away to Kepler-22b. It's nestled perfectly in its star's habitable zone, where temperatures are supposed to be just right for liquid water. The expectation we always see in the brochures is a beautiful, warm ocean world where you could just go for a nice swim. But the reality? Kepler-22b is a super-Earth. It's huge, which means it likely has an incredibly thick atmosphere. That thick atmospheric blanket creates unimaginably high surface pressure. So instead of a relaxing swim, stepping out onto this planet would cause immediate and fatal barotrauma, literally and violently collapsing your lungs. And that liquid water, under all that crushing pressure, it might actually exist in a supercritical state, which is this terrifying hybrid between a liquid and a gas.
And, just to rub salt in the wound, even if we developed some hypothetical warp technology that let us travel at 20% the speed of light, it would still take 3,175 years to make the journey. That is over 3 millennia just to find out this highly hyped ocean world is basically a completely unlivable pressure cooker.
All right, Section 3, the red dwarf danger, Proxima Centauri b. So what about Proxima Centauri b? It's our absolute closest neighbor, just 4 light-years away. But to really understand this planet, we have to understand its host star. It orbits a red dwarf star. Because red dwarfs are small and dim, the planet has to orbit extremely close just to stay warm. But orbiting that close results in a bizarre phenomenon called tidal locking. The planet rotates at the exact same rate that it orbits, meaning one side is permanently facing the star in endless, blistering daylight, while the exact opposite side is frozen in eternal, pitch-black night. So the crucial point for a real estate buyer is, where do you live? You live in the Terminator Zone. It's this narrow strip of permanent twilight, separating the frying pan from the freezer. It's supposedly the cosmic real estate jackpot, moderate temperatures, maybe even some liquid water. Sounds like the absolute perfect place to build a shelter, right? Yeah, not so fast. Here is the brutal reality. Red dwarf stars are incredibly violent. They constantly emit deadly, unpredictable solar flares and massive blasts of extreme ultraviolet radiation. Being that close to the star means these eruptions just blast the planet, literally stripping away the electrons and ions in the atmosphere until there's absolutely nothing left. So your cozy little shelter in the Terminator Zone would be left entirely airless and completely irradiated.
Section 4.
touring the TRAPPIST system, 7 Earth-sized worlds. Welcome to the TRAPPIST-1 system. It's 39 light-years away, featuring a tiny, ultra-cool red dwarf with 7 Earth-sized worlds crammed into an orbit that is smaller than the distance between Mercury and our Sun. This TRAPPIST tier list perfectly summarizes the sheer chaos of exoplanet exploration. We've got 7 planets, all tidally locked. Look at 1b, right near the star. It's essentially a 225 degrees Celsius pizza oven. 1c has thin air and hurricane-force winds. 1d blasts you with solar flares. Now 1e, that's the darling of the group, a prime Earth 2.0 candidate right in the middle of the habitable zone. But your entire year only lasts 6 days. Move further out to 1F, and you get cryovolcanoes. 1H, all the way at the edge, is just a frigid ice ball sitting at minus 100 degrees Celsius. But what about 1G? Well, TRAPPIST-1G represents a truly fascinating new class of worlds, a Hycean planet. High for hydrogen, Cean for ocean. It's entirely covered in deep water with a thick, warm atmosphere keeping it completely liquid. But remember, this is a super-Earth. The gravity here is intense. That means the water movement isn't just a gentle tide, it creates towering, terrifying, rogue waves that would crush absolutely anything we ever tried to build on the surface.
Which brings us to Section 5. The flora of Kepler 186f, habitable zone check.
We are traveling 579 light-years away now to Kepler 186f, which was actually the very first Earth-sized planet ever found in a habitable zone. What would it actually take to settle there? Well, here's our highly structured survival checklist. Step 1 is pretty obvious. You have to analyze the atmosphere, because even if it has oxygen, it might contain crazy hazardous alien compounds. Step 2, establish power. Now this presents a unique problem, because Kepler 186f orbits a dim red dwarf. It only gets a third of the light that Earth does. Standard solar panels simply won't work here. You'd literally need a portable nuclear generator. Finally, step 3, secure food. You can't just plant your potatoes in alien dirt. You need an advanced aeroponic system where roots hang in the air and are misted with recycled water and nutrients. But hey, even if you check all those boxes, you've got to consider these hidden hazards. The gravity is 30% stronger, which would completely exhaust you. The local liquid water? It's likely highly toxic. The alien flora might look beautiful, evolved specifically to absorb dim red light, but a single whiff of alien pollen or a touch of their sap could trigger fatal allergic reactions. And the weather? Because of the dense, chilly atmosphere, the rain can become super cooled. The instant a droplet hits your spacesuit, it explosively crystallizes into ice, flash freezing you right on the spot. Finally, Section 6, the Fermi Paradox explained. Where are they? This transitions us perfectly from the physical hazards of space to the ultimate philosophical question of our universe. With literally billions of planets out there, why are aliens so impossible to find? This is the famous Fermi Paradox. I mean, we've been seriously looking for alien life with radio telescopes for just over 60 years. Compare that tiny blip to the billions of years the universe has actually existed. The cosmic distances and timescales are so incomprehensibly massive that we may have simply just missed each other in the dark. But you know, there is another much more sobering answer to this paradox: the Great Filter Theory. This hypothesis suggests that advanced technology is essentially a ticking time bomb. The idea is that once a civilization becomes powerful enough to build rockets, they simultaneously invent the tools to destroy themselves, whether that's through nuclear war, engineered pandemics, or environmental collapse. It's a truly chilling explanation for why the cosmos seems totally empty of space-traveling civilizations. They just wipe themselves out before they can ever leave. And that grounds us right back into the reality of modern astrophysics with this fantastic quote. When scientists look for signs of life, they aren't actually looking for sci-fi civilizations to hang out with. They're looking for simple life forms. They are looking for marine phytoplankton in the oceans of K218b. They're looking for basic biosignatures, for sure, not flying saucers. And that brings us to our final takeaway. Finding an exact Earth 2.0 requires an astronomically rare cosmic balance. It's not just about being in the habitable zone. It's about atmospheric pressure, the specific type of host star, the gravity, the radiation, and a million other tiny variables that miraculously didn't flash freeze or irradiate us. When we summarize the brutal reality of these alien worlds, it leaves us with one really profound question. Instead of constantly searching the stars for a new home, shouldn't we be doing absolutely everything in our power to protect the fragile, miraculous balance of the only one we have?